All right, we're ready to perform machine learning in R. So what we're going to try to do is we're going to try to predict tissues based on gene expression data. And as we'll see later, we're going to make it a little bit challenging because it turns out that that's a very easy thing to do. Tissues have very different gene expression profiles. So we'll try to do it with fewer dimensions in all the genes. Now, before we start, I want to show you the outcome that we're trying to predict. It's tissue. Right, so we can see that there's one tissue, placenta, that only has 6. So I'm actually going to take that one out, and that way it gives us a little bit more balance, and it's better for illustration purposes. But there are ways to implement machine learning algorithms with cases like this. All right, so let's take out the columns with that tissue, the tissue placenta, and then we will define y, our outcome of interest, and x, our matrix of predictors. So y is just the tissue categories, and x is the transpose of E. Right? It's the transpose because each column now is a predictor. That's how these machine learning algorithms work. So we can see the dimension of x is the number of outcomes, 183. That's the length of y. And it has 22,215 predictors. Okay, now, the first thing we think about when we're getting ready to do machine learning is cross-validation. It's very important that we cross-validate our results, that we train on one set and test on another. So the first thing we're going to do is create a set of indices that facilitates cross-validation, and we're going to use this nice little function in the caret package, create folds, that automatically does this for us. All right, so it takes our outcome y's, and we're going to create 5 folds. So what it does is it splits the data into 5 groups, and now what we're going to do, which are called the folds, and what we're going to do when we come to the prediction part is we're going to leave out one fold, use the other 4 to train, and then test on that one we left out. That's the idea behind cross-validation. And then we do that for each fold. We leave out the first, the second, the third, the fourth, and the fifth. All right, now let's show you what the outcomes are in these 5 folds. So we have 5 folds, and in each one we have a series of tissues. These are the tissues in the 5 subsets, the number of tissues in each of the 5 subsets. You can see why we left placenta out. So a lot of these would have 0 placentas, and it would complicate the problem slightly. Okay, now, as I said earlier, we're going to make this problem more challenging by looking at only 2 dimensions. We're going to take the first 2 dimensions that is given to us by CMD scale. All right, so we're going to make a smaller set of predictor, basically 2, and we're going to try to predict tissues based on these 2 predictors. So I'm going to load the Rafalev package to make some nice looking pictures. And we can see what these 2 dimensions are. And there they are. And we have the different colors are the different tissues. So we're going to try to predict those colors based on these 2 dimensions. You can already see that it's not going to be easy because they don't separate out perfectly. All right, so let's get started. So I'm going to use KNN to do this, which is in the library class. And I'm going to apply KNN in the following way. What I do is I'm going to train on the rows, on all the rows except the ith fold. So here I'm doing the first one. So I'm going to take out the rows that are indexed in that first fold, take them out also for the outcome y. You can see here, CL gives you the outcome. And then we're going to test on the remaining data set. Okay, so that gives us back that we're going to get back results for this test data as well. So we don't use the indices in this fold to train the model. Right, so that's our test set. So we can run this really quick. It's very fast, and now we can see how we did it. Right, so we can look at the tissues and the actual tissues and the calls, and we can see, for example, that we made some mistakes for cerebellum. There's 2 mistakes here. I think we got all the colons right, but we got some errors in hippocampus, etc. Now we can just tally up all the mistakes we made here, right? We count how many mistakes we made, and we take the mean, and we see that 17% we made mistakes in 17% of our predictions. Now that was only one fold. Okay, so now the next step is to run through this, do the same thing we just did, do it now for every fold. Okay, so that's what I'm going to do now. I'm going to go along each of the 5 folds, right? This is just 1 through 5. See that there? And for each one, I'm going to run again what we just did. I'm going to run it again, leaving out now the first, second, third, fourth, and fifth fold, and then counting the number of mistakes we made, right? So we just run that. I'm going to do that for the first, sorry, I don't need this I anymore. Oh, where did I go? I'm sorry. Right down here. So I don't need to the I is set in sapply. And I do need to set K, because I'm leaving it general. You'll see why we're doing that in a second, to, let's say, 5. Right? So now we run it, and now we're doing, we're doing the cross-validation. Basically, we're testing and training, leaving out folds, and we're doing it for all 5. So we run this, should be pretty quick. And now we have in rest.k, the results.k, we can see we made 6 mistakes in each one of them. Okay, so now the next step is to compare the different k's. So we want to choose the number of nearest neighbors that we include. Is 5 a good choice? Should we have done 10? Should we have done 1? So before we continue with that, let's just write down here what the final outcome is. We sum up res k and divide by the length of y, and that gives us the error rate, right? 16% now. Right, so I'm going to do this now for every single, not for every single k, but for several k. So let's do 1 through 12. And now what I do is I add another level of another loop. So I go through the k's, function k, and I'm ready to apply what we just did for every single, for these 12 values of k, and see, and then we can plot them and see which one worked best. Okay, and then we close it. All right, so there, it's pretty fast. And now we can just plot k's against this stress and see how they compare. And we can see that the best choice actually was 5. And we can see that 0 makes more mistakes, and then it goes up. So that's how we use cross-validation to perform, to do prediction. With just two dimensions, we did pretty okay. 16% mistakes is not terrible. Now the last thing I want to show you here is that if we use more samples, if we use more than 2 dimensions, then it becomes pretty easy to do this. So we can see that if I now redo it with 5 dimensions instead of 2, we can see that let's wait for it to finish and then run it. So if we use 5 dimensions before we use 2 in the k nearest neighbors approach, then we do much better. We basically make no mistakes when we have more dimensions. So just with 5 dimensions, we're already doing a very good job. If we make it 100 or 1,000 dimensions, then we'll probably do perfect. Okay, so that's how you use cross-validation to test out machine learning procedures and also to pick the parameters.